In this video, we're going to study Lesson 2 in the Classical Liberal Arts Academy's Classical Arithmetic course. And I'd like to tell you up front that this is going to be a very difficult lesson. If you've tried to read the lesson on your own, you'll already know that it's very difficult to read, and there's a lot of information in this lesson that you're very likely not familiar with. So we're going to do our best in this video to walk through the content of this lesson, and I'll try to clear up some of the things that you can't be expected to understand at this point, and I'll try to help you understand what you need to study in order to eventually understand all of the content in this lesson. But most importantly, we want to get through Lesson 2 because this provides us with an introduction that allows us to move on to Lesson 3, and things actually get much easier in Lesson 3. So we just have a difficult lesson here in Lesson 2 because there's a lot of background information that you're not familiar with. So I'd like to walk you through some of this stuff and make sense out of this lesson and provide as much explanation or help as I can for you at this point. I'm just going to be honest. There's a lot of information in this lesson that you just can't be expected to understand yet. So the goal is to become familiar with it, to read through it, get a general sense of what the lesson contains, and then keep it in mind as you continue your studies and begin to study philosophy and learn to understand what is Pythagorean philosophy, which is just very, very foreign to modern students and thinking, and yet is something that we're going to have to learn if we're going to understand ancient philosophy. Okay, so in Lesson 2, we're studying sort of a history of ideas in arithmetic to help us get started with an introduction to number. I want to begin by discussing the goal of arithmetic, and I trust that I've explained this already to some degree in a video that I produced on an introduction to the quadrivium, and I probably talked a little bit about this in our first lesson in classical arithmetic. But we have to remember that this arithmetic that we're studying in classical arithmetic is philosophical or theoretical. It's not practical. If you take our practical arithmetic course or modern arithmetic, it's focused on counting physical objects. It's focused on calculation. That's what modern practical arithmetic is. But this is not modern practical arithmetic. This is ancient philosophical arithmetic. So we have to remember that the goal in ancient arithmetic was to study and pursue wisdom, wisdom itself, to be wise, to understand God and all that God has created. And arithmetic was considered one of the studies or sciences necessary in the pursuit of wisdom. So our goal in classical arithmetic is to think about the eternal things in the world, to think about God himself, to think about things that never change, that will always remain the same forever and ever. That's really the goal of arithmetic. In Plato's Republic, Socrates explains that arithmetic and geometry help us to raise our minds above the world that we see and feel through our senses to a world that is understood by the faculty of reason or intelligence. And it's that raising up from this world of change and birth and decay and corruption and death into the contemplation of a world of eternal things, of things that can only be understood by reason. It's that elevation of our thoughts from the sensible world to the insensible world that is the goal of classical arithmetic. So we need to keep that in mind as we get into this study. We're not trying to learn how to add and subtract dollars and cents. We're not trying to learn how to measure distances on Earth. We're not trying to measure time. We're not trying to calculate things. We're trying to understand the concept of number itself, which is eternal. So remember the goal of arithmetic. What the author does for us in chapter 2 is provide us with a bit of a history of teaching on the idea of number. So if we asked, what is number, which is the obvious question in arithmetic, if we ask what is number, the definition of number is not so simple. And the discussion and development of the definition of number was accomplished over hundreds of years by the work of a number of different philosophers. And so in our lesson, the author provides us with a bit of a history of the development of the philosophical definition of number. Okay? Now, as we go through this history, the ideas are difficult to understand because they're part of a philosophy. They're part of a system of philosophy that in modern times we're just not familiar with. It's Pythagorean philosophy. And until you're able to learn about the philosophy of Pythagoras and his followers, you're going to really struggle to understand these ideas because they sound crazy. And yet they're really not. It's just a different way of speaking, thinking about number, speaking about number, and so on. So let's just look at the details that are found in our lesson, and I'll try to make this as helpful as I can for you at this point in your studies. So in this chapter we have a bunch of names given to us, and these are all the names of ancient philosophers, and they all have something in common except for the first one. Okay, so let's just walk through this list of names and learn a little bit about who these people are. All of these names are right in your lesson, and I've added the dates that mark the lives of these different philosophers, so you'll have a general idea of when they lived and how they relate to one another. The first one that's named is the Greek Thales. Thales. And you can see here that he lived from 624 to 548 BC, so 600 years before Christ. 600 years before Christ. The city of Rome, just for reference, the city of Rome was founded in 753 BC, so Thales was born 100 years after the founding of Rome. That's when he lived. And what we read about in here and what we can learn from history is that Thales was a Greek who went to Egypt and learned the mathematical philosophy of the ancient Egyptians. And so the Greek philosophy concerning mathematics really is Egyptian philosophy that was learned by the early Greek philosophers and then brought back to Greece. So there's a connection in history that's very important, a connection between Greek philosophy and ancient Egyptian philosophy. And that's especially important because Egyptian history is tied into the history of sacred scripture in the Old Testament. And so we can see history of biblical events and history of secular philosophical events are connected in the history and philosophy of Egypt. It's especially important to note that Abraham in the Old Testament went down into Egypt at one point in his travels. And it's believed, according to tradition, that he actually brought Babylonian philosophy, Babylonian mathematics, down into Egypt with him, and he taught and revealed some of that to the Egyptians. Then later we read that Moses was born in Egypt and was adopted by a princess in Egypt, and he was raised and given an education in Egyptian philosophy. So now we have Abraham and Moses and Egypt and Greece all connected in an ancient mathematical philosophical tradition. And it's very important to learn about and understand. Obviously, we don't have time to explain all this or study all of this, but I'm going to tell you where you can get more information. So the first philosopher we'll learn about, Thales, lived 624 to 548 BC. And what we read here about Thales is that he defined number conformably to the doctrine of the Egyptians, by whom he was instructed to be a collection of monads. And we'll learn more about that in a minute, but the monad is simply the idea of one. Okay, so number was defined simply as a collection of ones, or a collection of units. That's how Thales defined number, a collection of units. Very simple. Next, the second philosopher that's named in our lesson is Pythagoras. Pythagoras. In English we call him Pythagoras. He is by far, in this list, the most important. Okay? Pythagoras is the Greek name, or Pythagoras as I say. He's the most important. He lived from 570 to 495 BC. So born in the time of Thales and died 50 years after the death of Thales. Pythagoras was also educated at some point in Egypt. So again, we have this connection of the Egyptian, Babylonian, Hebrew, and Greek philosophical traditions in this history. Pythagoras, let me say this before we go any further. If you'd like to learn, and I strongly recommend you study this book. There is a book written by Diogenes Laertios. Diogenes Laertios. It's a book available in English translation. I'll post a copy on the CLAA website. But this book provides a collection of biographies of the famous ancient philosophers. And so you can learn about these philosophers in great detail from this book, Diogenes Laertios, his Lives and Opinions of Ancient Philosophers. I think that's the title, Lives and Opinions of the Ancient Philosophers. So you can learn the biographies of all these. And in the ancient world, these men were like the saints. So their biographies were like the lives of the saints in the ancient world. And you can learn about these and many more of the ancient philosophers. And that's very, very important book that I strongly recommend you get a hold of and start reading through. But when we learn about Pythagoras, what we learn is that he was sort of a legendary, almost mythical character. He was a holy man, a wise man, given great gifts, believed to be a miracle worker, and much more. Very special man, and he was the founder of what's called Pythagorean philosophy. What all these men have in common, the names below Pythagoras here on this list, is that they're all followers of Pythagoras. Okay, so we basically have Thales, who's the first Greek mathematician with connection to Egyptian philosophy. And then we have the superstar, Pythagoras. And then all of these other men are followers of Pythagoras, except for the last one. Chrysophus, as you see here, it says he's a Stoic. We'll get to him a little bit later. But Pythagoras is the master of ancient philosophy, ancient mathematical philosophy. Now, what Pythagoras taught, which is the foundation for all classical mathematics and classical arithmetic, is that everything was created by number. And we talked about this in previous lessons. That number was the idea present in the divine mind by which all things were created. And again, at this point in your studies, if you're just getting started with classical arithmetic, you're not going to understand all these ideas. But what I want you to do is just learn them, become familiar with them, and then go and study the lives of the philosophers. And as we continue to work our way up through philosophy, eventually you can study the writings of Plato, because Plato was also a follower of Pythagoras, and you can learn more and more of this philosophy. It's not something that's going to be easy for you. It's going to take a long time. In this lesson, getting us into classical arithmetic, we just want to survey the development of the idea of number as the definition was developed over time. So don't worry about understanding everything. Just pay attention to the most important parts. Now, as we look at what Pythagoras has to say in our lesson, you're going to see it's very abstract and difficult to understand. And that's why I say don't worry about that right now. Just don't try to understand everything. Just learn. Just listen and absorb it and learn, because in the future it's going to make sense as you continue in your study of philosophy. But what our lesson says is Pythagoras defined number, and here this is very profound, abstract philosophical thought. Pythagoras defined number to be the extension and energy of the spermatic reasons contained in the monad. I'll read that one more time, and this is just a copy of the lesson here. Pythagoras defined number to be the extension and energy of the spermatic reasons contained in the monad. And as I said, this is profound philosophical teaching, and the way that you can understand these things is to read them and just study the meaning, or look the meaning up in a dictionary of each word in the definition. The extension, the energy of the spermatic reasons contained in the monad. So that's the definition according to Pythagoras. It also says, or otherwise, to be that which, prior to all things, subsists in a divine intellect, by which and from which all things are coordinated and remain conumerated in an indissoluble order. It's a lot of language, a lot of vocabulary, and I know it's difficult to understand. You can read it better in your printed lesson, but my goal in this video is simply to walk you through this little history that we're provided with, and then get to the main point of this lesson, okay? So Pythagoras defines number as that which, prior to all things, subsists in a divine intellect, by which and from which all things are coordinated and remain conumerated in an indissoluble order. It's a pattern. In a previous lesson we learned the word paradigm that existed in the mind of the Creator, by which all things were ordered and by which all things will remain ordered forever. It's indissoluble, okay? That's the Pythagorean idea of number in classical arithmetic. Next we go on and we read others of his philosophers define the number to be a progression from unity, or one, through the magnitude of it. And then we go on and read, but Eudoxos, who lived from around 400 to around 350 BC, Eudoxos, the Pythagorean, said that number is definite multitude, in which definition he distinguishes the species from the genus. So what that means is that he defines number as definite multitude. Multitude is the genus, that division of quantity. We talked about this in lesson 1. If we take quantity, it divides into two species, multitude and magnitude. Multitude then becomes a genus and divides into species. One of those species is definite multitude. That was established by the philosopher Eudoxos, okay, around 400 BC. So he established the species and defined number according to genus and species, a more philosophical, systematic definition. Next, we have the philosopher Hippasos. His followers, who are called the Akousmatiki. And again, we're not going to get into all this, but the followers of Pythagoras divided into two groups after Pythagoras' death. One group was this Akousmatiki, and the other group were called the Mathematikoi. All right? It's just historical information to become familiar with. Two divisions of the followers of Pythagoras, one of whom was the Akousmatiki, and their leader was Hippasos, who was himself a follower of Pythagoras. Our lesson tells us he said that number is the first paradigm of the fabrication or creation of the world. So we've already seen that that was taught by Pythagoras, the idea that number is the idea or the pattern by which the Creator designed and made all things. He also said that it is the judicial instrument of the God who is the demiurgus of the universe. The judicial instrument of the God who is the demiurgus of the universe. That's Hippasos, okay? A follower of Pythagoras, the leader of the Akousmatiki, one of the divisions of Pythagoras' followers. Next we have Philolaos, who lived from 470 to 385. And just note that these are not in historical order, okay? Eudoxos came after Philolaos, all right? But in the order that they're presented in the lesson, they're not in historical order. But Philolaos says that number is the most excellent and self-begotten bond of the eternal duration of mundane natures. A lot of vocabulary, but we're going to see what this means in a little bit. All right, and that wraps up this sort of introduction to the history and development of the definition of number among the Pythagorean philosophers. And we see the dates are from around 600 BC down to 350 BC. So 600 to 350 BC. And just for reference, you can see that I wrote on the board here abbreviations for Socrates, Plato, and Aristotle. Socrates lived about the same time as Philolaos. Okay, 470 to 385. Those are just about the same years that Socrates was alive. Plato lived just after that, and Aristotle just after him. So as you look at this history of the Pythagoreans, they're called pre-Socratics because they come before Socrates, Plato, and Aristotle, who become the most famous of the Greek philosophers. All right? So these ideas of number in classical arithmetic are developing before the classical age in Greece, where Socrates, Plato, and Aristotle show up. Okay? This is the foundation of Greek philosophy, and what's very important is to remember that it has a connection to Egyptian philosophy. Okay? Remember that. That's the summary of the definition of number, and then in the second part of the lesson, we go into the definition of the monad. Right? The monad is the idea of one, which is very important in Pythagorean philosophy, the idea of one. And we'll understand why in a few minutes. But as we try to define what one is, okay, think about that. You know, you can close your eyes and just meditate and try to think, what does one really mean? What is one? What makes something one? And try to get the idea, the true essence of oneness in mind, and so that you could define one. It's very difficult, actually. Well, these philosophers worked on that in ancient philosophy. We read, the monad is in discrete quantity that which is the least. It's the smallest or the least number of discrete quantity. Remember, who was it that defined, Eudoxos defined number as definite multitude. Well, if we take all of the different numbers, all of the different definite multitudes, we ask which is the least. We could define the monad by saying it's the least definite quantity or definite multitude. Discrete quantity, same idea. The monad is in discrete quantity, that which is the least, or it is the first and common part of discrete quantity, or the principle and source of it. Our next name is Thymaridas, or Thymaridas in Greek. He lived from 400 to 350. He's the next named here, and we read, according to Thymaridas, indeed, the monad is bounding quantity. Bounding quantity. What does that mean? Since, it says, the beginning and end of everything is called a bound. Now, what happens here, and why this gets a little confusing, is because arithmetic and geometry come together. And let me just quickly show you what this means. If you were to ask, what does the number 1 have to do with bounding quantity? Because the beginning and end of everything is called a bound. What in the world does that mean? Well, this idea of number and the idea of magnitude in geometry begin to mix a little bit. And this is where these ideas come from, how we move from talking about number to talking about the creation of the world and all different bodies and things like that. So just to make this clear, I hope, in a simple way, I think you can see over here. If we take the monad, or number 1, and imagine it as a point, 1 point. Okay, we have the point, which is the first figure we learn about in geometry. So let's use a point to symbolize the monad, or 1. Now, the next number in definite multitude would be 2, which in the Greek system was called the duad. Okay, so we'd have the monad and the duad, 1 and 2. We'd have 2 points. Okay, we have a number, 2 points. But in geometry, we learn that anytime we have 2 points, we can connect them and form a line. So we start with 2 points, the number 2, a multitude. But then we connect the 2 points with a line. And now we have both magnitude and multitude. We have 1 magnitude, this line. And we have a multitude of 2 points. So we have 1 and 2 present in the same figure. The monad, if you look, is the bound, or the termination, the end point of the line. So the monad is the bounding quantity. All right, that's where this idea of bounding quantity comes from. So just to repeat that, Pythagoras said that the monad is bounding quantity since the beginning and end of everything is called a bound. And we learn that in our definitions in Book 1 of Euclid's Geometry. We go on in the lesson to read, in certain things, however, as in a circle and a sphere, the middle or center point is the bound. It's just clarifying that not everything is bounded on its ends. A circle or a sphere, the center point is called the bound. But those who are more modern, we read, and remember, Pythagoras was writing from around 400 to 350 BC, so more modern doesn't mean, last year. It means more modern than 400 BC. Okay, so those who are more modern define the monad as that according to which everything that exists is called one. And this is a more modern definition of one that we might find in a modern practical arithmetic book. The monad is that idea according to which everything that exists is called one. So if I said, this is one eraser, one paper, that idea that allows us to call this one and this one, what they have in common as one, is the definition of the monad, or one. Next, the followers of Chrysophus. Chrysophus was a Stoic philosopher, all right? So not a Pythagorean philosopher. He was a Stoic philosopher who lived from 279 to 206 after Socrates, Plato, and Aristotle, okay? Chrysophus. The followers of Chrysophus assert confusedly that the monad is one multitude. Now, he says confusedly because it seems that things are mixed together. How can there be one multitude? One multitude. Well, when we look here, we get an idea of how you can have one multitude. I'm not saying that this is the idea that Chrysophus has in mind, but we see this idea of a single multitude, and even the author says that the followers of Chrysophus assert this confusedly, all right? That monad is one multitude. For the monad alone is opposed to multitude. And then we go back to the Pythagoreans. But certain of the Pythagoreans said that the monad is the confine of number and parts. Now I'm going to illustrate this for you in a minute. The Pythagoreans said that the monad is the confine of number and parts, for from it, from the monad, as from a seed and an eternal root, ratios are contrarily increased and diminished. And again, when we get into Pythagorean philosophy, the language just becomes very strange and unfamiliar, and it takes it's going to take time. You're going to have to study Pythagorean philosophy to understand the ideas, and we don't have time to get into all of this in an introductory arithmetic lesson. But I can illustrate and show you what he's referring to. Okay, what is this idea of these Pythagoreans? Well, try to follow me here, All right, and you can watch this again, so don't stress out if things get a little confusing. If we think about a multitude, multitudes begin at one, or unity, or the monad, and they multiply. They multiply. So we have numbers: 1, the monad, 2, 3, 4, 5, 6, and so on. And each number of a multitude, as we increase our numbers, can be thought of as a ratio of a multitude to 1. So the number 2 can be thought of as a ratio 2 to 1. 2 to 1 and 2 express the same idea. 3 can also be thought of as 3 to 1, 4 as 4 to 1, 5 is 5 to 1, 6 is 6 to 1, and so on. So we can think of multitude as a series, or the numbers that express multitude as a series of ratios. All right? The ratios can be contrarily increased, as we see with multitude. I'll just write mult here for multitude. Okay, so the ratios increase when we look at multitude. But if we look at magnitude, the number 1 as a number can't be divided. It can't be divided. It's the first of all numbers. It's the least of the definite quantities. Okay, we can't divide beyond 1. Any multitude is made up of parts which break down to 1 as the smallest part. We can't divide beyond 1. The only way that we can divide something that's 1 is if we take one magnitude and divide it into parts. Okay? And when we work with magnitudes, if we start with 1, that's a whole. 1 to 2 is like a half. 1 to 3 is a third. 1 to 4 is a quarter. 1 to 5 is 1/5. 1 to 6, and so on. We see that as the parts diminish in magnitude or size, the numbers in the ratio that are compared to the monad or 1 increase. 1 to 2, 1 to 3, 1 to 4, 1 to 5, 1 to 6. The numbers of the parts increase, the size of the parts decrease. And so we have this contrast between multitudes and magnitudes, and the ratios of the multitudes to the parts of a magnitude. And again, I know this is complicated and unfamiliar, and I'm not asking you to really understand all this. I'm just illustrating for you simply the ideas that are being spoken of in this lesson. The goal of this lesson is really not that you learn and understand all these ideas. We're going to lead up to a final definition for our course of number and the monad. And the author is simply leading you through the history of the development of these ideas. Okay, you're going to have to study philosophy, Pythagorean and Platonic philosophy, to get into all these ideas. But the goal of this lesson is for us to simply see how these ideas were worked out and developed over time, so that as we get into our study of classical arithmetic, we can begin with a good definition of number and of monad, so that we can begin our studies and have an established definition. All right? So that brings us to the end of that second part on the monad. And then as we continue on in our lesson, we have this paragraph that begins, the monad, therefore. And so now we're sort of coming to the end of this lesson and summarizing what's been said and developed by all the ancient philosophers, so that we can wrap this up and move into our first real lesson in classical arithmetic. The monad, therefore, and you can see I have this written up here. So I'm going to erase this just to make things clearer. Okay? What we see now in our lesson I've got here summarized on the board, because this really is the point and the focus of lesson 2. The monad, therefore, is the principle and element of numbers. The monad is the building block, the principle and element of all numbers, which, while multitude is diminished by subtraction, is itself deprived of every number and remains stable and firm. So while multitudes change by subtraction, for example, or by addition, remember the definition of quantity that we often learn is anything which may be increased or diminished. While multitude increases and diminishes, while number changes, monad, or one, always remains the same. It doesn't change. It's always stable and permanent. The idea of one, right? The monad is the principle and element of the numbers. While multitude is diminished by subtraction, the monad itself is deprived of every number and remains stable and firm in itself, because it is not possible for division to proceed beyond the monad. If we divide the one, okay, now let me diagram this. I gave you the example before of the 2 points and the line. Let me just say that if we add a third point, we can now connect these dots in geometry, and we have a triangle. If we have a fourth point, we can create a pyramid and so on. The point being that there's a relationship between the collection of monads and the figures, the geometrical figures or bodies. That's what this is beginning to reference. And as I said, we start to mix arithmetic and geometry, and for you getting started, that gets confusing. But it's really not a confusing idea. The lesson says, if we divide the one which is sensible, what it means, the one which is sensible, means one body, one figure. It's sensible. That means we can perceive it, we can see it. Okay? One point, the idea of one itself would not be sensible. You couldn't see a point. A point has no breadth, no width, or no length, no width, sorry. But when we have 2 points, we all of a sudden have a line. And when we add a third point, we all of a sudden have length, breadth, and depth, okay? Actually, let me just clarify that. When we have 2 points, we have length and no breadth. When we add the third point, then we have length and breadth. And that creates what in geometry we call a superficies, which becomes sensible, okay? I'm sorry if that was a little confusing. I misspoke there, and I mentioned 3 dimensions, where with 3 points, there are only 2 dimensions. There's length and breadth, okay? If we divide the one which is sensible, which is insensible, into parts, the one becomes a multitude because it's broken into parts. It begins as one sensible magnitude. But if we divide this into parts, there's then a multitude of parts. Again, the one becomes multitude by the division of the one into parts. And by a subtraction of each of the parts, if we take away one part at a time, we'll end again with 1. We'll go back to unity, or the monad. If we again divide this one into parts, the parts will become a multitude again. And by an ablation, which just means taking away, same thing as subtraction, by an ablation of each of the parts, we shall at length arrive again at 1. So that 1, so far as 1, that is, as a number, is both divisible as a magnitude, it can be divided into parts, but also indivisible as a number, it cannot be divided. 1, this is an important principle, 1, as far as it is 1, is both divisible as a magnitude, and indivisible as number. For another number, when divided, is diminished and divided into parts less than itself. Thus, for instance, the number 6 may be divided into 3 and 3, or into 4 and 2, or into 5 and 1. But 1, and again notice it says insensible things, sensible things are magnitudes, but 1, insensible things, if it is divided as a body, it is diminished in size, and by section is divided into parts less than itself, but as a number, it is increased because it multiplies from 1 magnitude into parts, each of which is counted as a separate magnitude. Instead of the one whole, it becomes many parts, so that according to this, 1 is divisible. For nothing in sensible things which is divided into parts greater than itself. But that which is divided into parts greater than the whole, and into parts equal to the whole, is divided as number. Thus, if the 1 which is insensible things is divided into 6 equal parts, as number indeed, it will be divided into parts equal to the whole, namely into 1, 1, 1, 1, 1, and 1, 6 equal parts. And also into parts greater than the whole, namely into 4 and 2. When it says greater than the whole, it means the number of the whole, which is 1, is divided into 6 parts. If we divide it into 4 parts and 2 parts, the number of the parts is greater than the number of the original magnitude, which was 1. Again, I know this is a confusing idea, but that's what's being expressed here. Hence, the monad as a number is indivisible. But it is called the monad either from remaining immutable, which means unchangeable, and not departing from its own nature. For as often as the monad is multiplied into itself, it remains the monad. 1 times 1 is 1. 1 times 1 times 1 remains 1. 1 times 1 times 1 times 1 times 1. As often as you'd like to multiply the monad by itself, it remains 1. If we multiply the monad to infinity, it still continues to be the monad. Or it is called the monad because it is separated and remains by itself alone, apart from the remaining multitude of numbers. So that's where the idea of the monad comes from. That's what the name means. It has to do with remaining stable and firm and having this character of unchanging, immutable is the word the lesson uses, unity. Okay? That's the idea of the monad, or one. Then in the last paragraph, to wrap things up, since therefore number is the connective bond of all things, it is necessary that it should abide in its proper essence. Since number is the connective bond of all things, it is necessary that it should abide in its proper essence with a perpetually invariable or unchanging sameness of subsistence, and that it should be compounded, but not of things of a different nature. For what could conjoin the essence of number, since its paradigm joined all things? But it seems to be a composite. Number seems to be a composite from itself. Moreover, nothing appears to be composed from similars, nor yet from things which are conjoined by no analogy or comparison, and which are essentially separated from one another. Hence it is evident, since number is conjoined, that it is neither conjoined from similar things, nor from things which mutually adhere by no analogy. Hence, and this is the conclusion of the lesson, the primary natures of which number consists are the even and the odd, which by a certain divine power, though they are dissimilar and contrary, though even and odd are contrary, they flow from one source and unite in one composition and modulation. Now, that's a very difficult lesson with a lot of vocabulary, and I'm not asking you, I'm not encouraging you to try and seek mastery of all of the content in this lesson at this point in your studies. The point of this lesson, the purpose of this lesson, is to help us to understand how the ancient philosophers defined number, how they defined the monad, or one, which is the principle and element of all numbers, and then to conclude with this division of numbers, with the true division of number into its two species, even and odd, or odd and even. All right? So we have number defined by the ancient philosophers. We have the idea of the monad defined, and we learned something of the mystery of the nature of numbers and of the number one in particular. And then we have the philosophical division of number into its two natural or true species, even and odd. And when we get into lesson 3, we're going to begin studying even and odd numbers. Okay, so a very difficult lesson. No way that you're going to understand that in any masterful kind of way. What I want you to do is read it, watch the video as many times as you need to, become familiar with the ideas, and see the simple summary. We want to define number, we want to define monad, and we want to understand the division of number into even and odd, so we can begin our study of classical arithmetic. Unfortunately, this lesson comes at the beginning of classical arithmetic, when you're just getting started with this study, the first of the studies on your path to philosophy. And I don't know how you would make it through that lesson without some help. And even here in this lesson, which is almost an hour long, we really barely touched on each of the points as we went through it. But I hope that's a helpful introduction to lesson 2. And I encourage you to work through the written lesson, study it as best you can, and get ready for the study of even and odd numbers beginning in chapter 3.